So now let's take some of the problems based on Breton cycle. So now we will discuss problems based on Breton cycle, that is gas turbine cycle. That is also very important from that point of view. So first of all, I am taking one problem. So here first I will write the problem and then I will solve the problem. In a gas turbine plant, in a gas turbine plant working on the Breton cycle, working on the Breton cycle, Breton cycle with a regenerator of with a regenerator of 75% efficiency, 75% effectiveness, regenerator of 75% effectiveness. The air at the inlet to the compressor, the air at the inlet to the compressor of the compressor is at 0.1 megapascal, 30 degrees centigrade. The pressure ratio is 6. The pressure ratio is 6 and the maximum cycle temperature is maximum cycle temperature is 900 degrees centigrade. If the turbine and compressor and compressor have each an efficiency of 80%, then find the percentage increasing cycle efficiency percentage increase in cycle efficiency due to regeneration. So in that problem we have to consider two cases, with a regenerator and without regenerator, and then we have to see what are the difference in the cycle efficiency. So now let's solve this problem. So I am giving the solution of this problem, and remember one thing, we have already discussed what is the meaning of regeneration and reheating. So we can also apply in case of Breton cycle. So first of all, I will write the given data. P1, that is pressure at the inlet of the compressor, that is 0.1 megapascal. Temperature at the inlet of the compressor, that is 303 Kelvin. It is 30 degrees centigrade. Maximum temperature, that is 900 degrees centigrade. Then if we add 273, we will get 1173 Kelvin. And here pressure ratio is given, that is 6, and efficiency of turbine and efficiency of compressor is given 80%, that is 0.8. So now we will discuss the process on the TS diagram, so it will be very helpful in understanding the problem clearly. So now I am drawing the TS diagram. It's TS diagram, and as we already told, in gas turbine cycle there is no phase change, so we will not see the dome. These two are the constant pressure lines. So now from 1 to 2s, that is our isentropic compression. That is our ideal 1 to 2s. And then if we go like that here, 3 to 4s, that is isentropic expansion. It is again ideal process. And again 4s to 1, this one is the heat exchange in condenser. So here I will again repeat 1 to 2s isentropic compression, 2s to 3, that is constant pressure heat addition, 3 to 4s isentropic expansion, 4s to 1 constant pressure heat rejection. So this one is the ideal cycle, means without regenerator. So I will write 1 2s 3 4s 1. This one is nothing but our ideal cycle without regeneration. So now if we take an example of actual cycle, so I will show the actual cycle here. In actual cycle, what will happen? There will be no isentropic compression, there will be no isentropic expansion. So entropy will increase in both the cases. So it will be like that. So now we are having 1, 2, we are having 1, 2, 3, 4, 1. So that is actual cycle without regeneration. So I will write actual cycle without regeneration, because we are not considering a regeneration in these two processes. So this is represented by 1, 2, 3, 4, 1. So that is the cycle, actual cycle without regeneration. So now let's take a case of regeneration. So in regeneration, what the things will happen? The gas which is coming out from the turbine is not directly going into the condenser. It is using in it is using for heating the gas before going into the combustion chamber. So what will happen? Suppose due to this process, expansion process, it is coming at 4s or either at 4, which is at the temperature. But if we are using for regeneration, then before entering into the condenser, the temperature of the gas will decrease. So we will get the state here at 0.5. So now it's very clear from this situation here, because now for actual and ideal we are at 4 and 4s, but if we are using regenerator, then some of the heat of the steam of the gas coming from the turbine is using in heating the gas before going into the combustion chamber. So that's why the temperature is decreasing. It is coming at 5. Similarly, due to the regeneration, the temperature of the gas which is entering into the combustion chamber will increase. So in actual process we are having at 2, in ideal process we are having at 2s. In both the cases we are having without regeneration, but due to regeneration we will be at suppose 0.6. So this one is the real representations of the ideal cycle and actual cycle without with regeneration. So I will write ideal cycle with regeneration So in both the cases we will see it is due to the regeneration, ideal cycle with regeneration. So we are starting from 1, 2s, and then we will go to 6, we are having 3, we are having 4s, we are having 5 and then 1. So 1, 2s, 6, 3, 4s, 5, 1. That is ideal cycle with regeneration. Similarly, we can write down actual cycle with regeneration. Regeneration. So now the cycle will be 1, 2, 6, 3, 4, 5, 1. That is actual cycle with regeneration. So now I will say it is now clear the representation of ideal and actual cycle with and without regeneration. So now let's take a case without a regenerator. Without a regenerator. So I am considering the case without a regenerator. So without a regenerator, so we are having two things here. The actual process 1, 2s, 3, 4s1, and uh, without regeneration, actual process will be 1, 2, 3, 4, 1. So for isentropic expansion or isentropic compression, we can use the reversible adiabatic law. So from graph we can say 1 T2 S by T1 equals to P2 by P1 to the power gamma minus 1 by gamma. So here the same thing I can write here for T3 plus to T4S, because if you see the pressure ratio, if you go for T3 T4S or T2S T1, the pressure ratio is same. So now we are having this P2 by P1 pressure ratio 6, gamma is 1.4 minus 1 divided by 1.4, so I will get 1.668. So T2S I will get 303 into 1.668, so 505 Kelvin, that is the T2S. So T2S will be 505 Kelvin. In similar manner, I can also calculate T4S. So T4S will be 1173 divided by 1.668. So it is coming 705 Kelvin. So now we are having T2S and T4S. So now let's calculate T2, and let's calculate T4. So we are having the efficiency of compressor and turbine. So we know the compression efficiency is nothing but T2S minus T1 divided by T2 minus T1. So now T2 minus T1, I can write T2S minus T1 divided by efficiency of compressor. So T2S we have already calculated 505, T1 we are having 303, and the compressor efficiency is given, that is 0.8, so it is coming 252 Kelvin. So in similar manner we can also calculate the T4, but here we are having T2 minus T1, so T2 will be 252 plus T1, so 252 plus 303, it will come 555 Kelvin. So T2 is 555 Kelvin. Similar way, we know the efficiency of turbine is nothing but T3 minus T4 divided by T3 minus T4S. So now I can write T3 minus T4 equals to efficiency of turbine into T3 minus T4S. So now we are having efficiency of turbine 0.8. T3 we are having T3 value, that is 1173, and T4S it's nothing but 705, so we will get the value 375 Kelvin. So now we are having 375 Kelvin. So but we are interested in T4, so T4 will be T3 minus 375. So 1173 minus 375, it will be 798 Kelvin. So these are the things for T2 and T4. So now let's calculate the turbine work and compressor work. So turbine work, it's nothing but H3 minus H4, H3 minus H4. So in terms of Cp, we can calculate by Cp T3 minus T4, and Cp for the gas we are having 1.005. T3 minus T4 we have already calculated, that is 375. So 375 will come 376.88 kilojoule per kg. Similar way, compression work, that is H2 minus H1, and in terms of Cp, T2 minus T1 equals to 1.005, and T2 minus T1 we have already calculated, that is 252. So 252 we will get 253.26 kilojoule per kg. So now we are having compression work. Similar manner we can calculate heat addition, that is Q1. Q1 is nothing but H3 minus H2. So in terms of Cp, that is T3 minus T2. So 1.005. T3 we are having 1173, and T2 we are having 555. T2 we are having 555. So it will come 621.09 kilojoule per kg. So now we are having Q1. So now let's calculate the efficiency. So efficiency nothing but W net, which is WT minus WC divided by heat addition, it is Q1. So 376.88 minus 253.26 divided by Q1 621.09. So it will come 0.199, or we can say that 19.9% without a regenerator. So now let's consider with regenerator. So now with regenerator. So with regenerator we have to calculate some of the values. So regenerator effectiveness is key one. So I will write regenerator effectiveness. So it is nothing but temperature difference in T6 minus T2 divided by T4 minus T2. T4 minus T2. That is the regenerative effectiveness. T6 minus T2, that is the actual temperature gain before entering into the combustion chamber, because the gas leaving at the compressor it is 2 at 2 point, but it is leaving with the regenerator at 0.6. So that is the actual temperature gain, that is T6 minus T2. So now the T6. So if we talk about this T6 value, so what will be the maximum temperature gain we can get? So in maximum temperature gain condition, whatever the exit temperature of the turbine and the entering temperature of the at the combustion chamber, it should be same. Means for maximum temperature gain, the temperature at the exit of the turbine, that is at T4, and temperature at the entering of the combustion chamber, that is T6, means at place of T6 I can put T4 for maximum condition. So we can get effectiveness. It is mentioned in the problem, it is 75%. So now let's take 0.75. So now T6 minus T2 we are having 555 equals to 0.75. T4 I am having 798 minus T2 I am having 555. So by this way I can calculate T6, that is coming 737.3 Kelvin. So now I can calculate Q1. Q1 is nothing but S3 minus S6. So Cp T3 minus T6. So Cp is 1.005. T3 is 1173 minus T6 is 737.3. So this value will come Q1 equals to 437.88 kilojoule per kg. So the Q1 will come 437.88 kilojoule per kg. So before further solving, I am writing the important fact regarding a gas turbine. So important fact regarding gas turbine. Gas turbine. So I will write here in gas turbine due to regeneration regeneration work output will remain same will remain same. Why I am writing this fact? Because in case of Rankine turbine, due to regeneration, the work output will decrease. Because in the Rankine cycle, due to the regeneration, the mass is the steam that is extracted from the turbine. So mass in each and every step is decreasing. That's why the work output is decreasing. But in case of gas turbine, there is no such phenomena. So due to regeneration, remember one thing: in gas turbine, work output will remain same. Only efficiency will increase. Efficiency will increase. So I am again repeating: in gas turbine, due to regeneration, work output will remain same. Only efficiency will increase. So now let's again calculate the efficiency. So efficiency will be W net divided by Q1. So W net will be same 123.62, and we have already calculated Q1, that is 437.88. So now it is coming 0.2837 or 28.37%. So now we have proved this thing. With regeneration, the efficiency is coming 28.37, and without regeneration, the efficiency was coming 19.9. Means there is an increase in efficiency due to the regeneration. So now let's calculate percentage increase due to regeneration. So I will calculate percentage increase due to regeneration. So in that we are having efficiency 0.2837 minus without regeneration we are having 0.199 divided by without regeneration 0.199. So it is coming 0.4256 or it is coming 42.56%. So due to regeneration, the efficiency is increasing by 42.56%. Now let's take another problem which is based on gas turbine. So I am writing the problem here first. A gas turbine plant operates on the Breton cycle between T minimum, that is 300 Kelvin, and T max, that is 1073 Kelvin. Find the maximum work done per kg of air and the corresponding cycle efficiency and the corresponding cycle efficiency cycle efficiency. How does this efficiency how does this efficiency compare with the Carnot cycle efficiency? Compare with the Carnot cycle efficiency operating between the same two temperature. Operating between the same two temperatures. So now let's solve this problem. So here in that problem we are interested in maximum work done per kg of area. So in Breton cycle, for maximum work done we are having the formula, that is Cp under root of Tmax minus under root of Tmin whole square. So we are having the value of Cp, that is 1.005. Tmax it is mentioned, that is 1073. T minimum it is mentioned, it is 300 square. So now we are having 1.005 into, if we solve it, 15.43 square, so we are having 239.28 kilojoule per kg. 239.28 kilojoules per kg. Now we will find out the cycle efficiency. So cycle efficiency in that case will be, we know for maximum work done, the cycle efficiency is 1 minus T minimum under root of T minimum by T max. So we are having 1 minus under root of T minimum is 300 divided by T max 1073. So we are having 0.47, or we can say that 47%. That is the cycle efficiency corresponding to this maximum work done. And now we have to compare this efficiency with the Carnot cycle efficiency. So let's calculate the Carnot cycle efficiency. Efficiency of Carnot, we are having the formula 1 minus Tmin by Tmax. So 1 minus 300 by 1073. So it will come around 0.721, or we can say that 72.1%. So now let's take the ratio, efficiency of cycle divided by efficiency of Carnot cycle. So efficiency of cycle we are having 0.47, efficiency of Carnot cycle we are having 0.721. So this ratio will come 0.652. So this one was the straightforward question, but remember all these formulas related to maximum work output at corresponding efficiency and maximum efficiency in terms of Carnot cycle. So it will be very easy if we apply the correct formulas. Let's take another interesting problem. So first of all, I am writing the problem here. Consider an ideal jet propulsion cycle. Consider an ideal jet propulsion cycle in which air enters the compressor at 1 atmospheric pressure and 15 degrees centigrade. The pressure leaving the compressor leaving the compressor is compressor is 5 atmospheric 5 atmospheric pressure, and the maximum temperature is and maximum temperature is at 70 degrees centigrade. The air expands in a turbine. The air expands in the turbine to such a pressure that that the turbine work is just equal to is just equal to the compressor work. The compressor work. On leaving the turbine, on leaving the turbine, on leaving the turbine, the air expands. The air expands reversibly and adiabatically, reversibly and adiabatically, adiabatically in a nozzle to 1 atmospheric pressure. To 1 atmospheric pressure. Determine the velocity of air. Determine the velocity of air. Velocity of the air leaving the nozzle. Leaving the nozzle. Now let's solve the problem. So I am here solving the problem. First I will draw the diagram for the jet propulsion plant. So in jet propulsion plant we are having a few things. We are having the diffuser. I will write here block diagram. Diffuser, air will enter here from diffuser and it will go to the compressor here. So this one is the compressor. See, it is at point 2 and it is leaving at point 3 and it is entering into the combustion chamber. It will enter into the combustion chamber, that is CC, and it will leave the combustion chamber at 4 and entering into the turbine. Here the compressor is coupled with the turbine and the gas will leave at point 5 from the turbine and it enters into the nozzle. We will enter into the nozzle and we will get the high velocity gas at point 6 which is leaving the nozzle. So this one is nozzle. This one is diffuser. So in our problem we are saying a diffuser is a part of compressor because the diffuser is not mentioned here. So for our problem we will say this whole assembly will be like a compressor. So I will draw the TS diagram here and I will show all the processes. So I am drawing the TS diagram. On y-axis there is a temperature, on x-axis there is entropy, and here I am having the pressure lines. These are the pressure lines here. So now from problem 1 to 2 we are in diffuser. 1 to 2 and 2 to 3 there is a compression. But here in our problem we are considering the diffuser is a part of compressor. So 1 to 3 there is a compression for us. 3 to 4 we are having the constant pressure heat addition, that is from 3 to 4. 4 to 5 there is a 4 to 5 there is a isentropic expansion in the turbine, that is from 4 to 5, and from 5 to 6 here in nozzle there is again uh, isentropic expansion, that is from 5 to 6, and 6 to 1 again this condenser. So 1, 2, 3, 4, 5, 6. This one is the process here. Here we are adding the heat. Here we are rejecting the heat Q2. So these are the typical representation of a jet propulsion plant on TS diagram. So now let's solve the problem here. So in our problem, we are considering the diffuser, the part of compressor. So now let's take P1. We are saying which enters at the compressor. So 1 atmospheric pressure. T1 is given 288 Kelvin, that is 15 degrees centigrade. P3 is given, that is 5 atmospheric pressure. And T4 is given, that is maximum temperature T4, that is at 70 degrees centigrade. And Kelvin we have to add 273, so it will come 1143 Kelvin. So now we can use the reversible adiabatic process formula. So T means 1 to 3, that is a here 1 to 3, it's a reversible adiabatic process, so I can use the formula for that. T3 by T1 equals to P3 by P1 to the power gamma minus 1 by gamma. So P3 by P1, that is 5 atmospheric by 1, gamma minus 1, that is 1.4 minus 1 divided by 1.4. So now we are having 1.58. So T3 will be 1.58 and T1 we are having 288. So T3 we will get 455 Kelvin. So we are having T3 455 Kelvin. Now in the problem it is mentioned the compressor work and the turbine work is same. So it is mentioned WC equals to WT, and we know in terms of Cp and temperature formula compression work is Cp, T3 minus T1, and turbine work is Cp, T4 minus T5. So Cp cancel out. T3 is 455 minus T1 288. T4 1143 minus T5. So by this way we can get the value of T5, that is 976 Kelvin. So the T5 will be 976 Kelvin. So again if we apply the reversible adiabatic process for the 4-6 process, now I will apply for 4-6 process. So I am having T4 by T6 equals to P4 by P6 gamma minus 1 by gamma. Again the pressure ratio is same, that is 5. So 1.4 minus 1 divided by 1.4, we will get 1.58. Same thing. So T6 will be 1143 divided by 1.58. So T6 we will get 725 Kelvin. So now I am having the temperature at state 6, that is 725 Kelvin. Now, but we are interested in this problem we are interested in velocity of air leaving the nozzle. So now assume the velocity of air, the velocity of air entering the nozzle, entering the nozzle is very small, is very small. So now by steady flow energy equation for nozzle, I can write H5 equals to H6 plus V6 square by 2 by neglecting velocity of air entering the nozzle. So now V6 square by 2, that is velocity of air leaving the nozzle, denoted by V6. We are having H5 minus H6. So H5 minus H6 in terms of Cp will be Cp T5 minus T6. So 1.005, T5 is 976 minus T6 is 725. So I will get V6 square by 2 plus 2, 252.26. So now we are having V6 equals to 2 into 252.26 into 10 to the power 4, because we have to convert all these things into meter per second. This quantity will come in kilojoule per kg. So V6 will be 2 into 252.26 into 10 to the power 4, and if we solve it, I will get the value of V6 equals to 710.3 meter per second. So the correct answer, the air leaving the nozzle in jet propulsion, is 710.3 meter per second.